Yesterday we started talking about energy, and I want to talk a bunch more about that. Before we do that, though, let's just do a little bit of review. So I want to know, what is the push or pull on an object that can cause it to accelerate called? Take a minute, think about it. Do you have an answer? Mass, force, density, or speed? Push or pull causes acceleration. That's definitely force. Okay, so remember, push or pull means that it is a force, and that's what causes things to accelerate. Things can't accelerate if they haven't been forced in a certain direction. What is the unit? Do you guys remember what the units for force is? Who's the guy that kind of did all the work with it? Well, his name is Newton, so that's who it's named after. So those are the units for force. Newtons, we just use a capital N. All right, so we are moving on to forms of energy now. Because like I said, we started talking about energy and how it was related to work. Now I really want to talk about all the different types of energy that we have. So we have chemical energy. So this is the potential energy stored in chemical bonds of compounds, right? So this is the potential for a chemical change and a chemical reaction to happen. We have electrical energy. This is work done by moving charges, which are electrons. Okay, so if an electron is moving, it's creating electrical energy around it. And this is also linked to magnetism. And if you want to know more about that, well, you just have to take Physics 30 in a couple of years. So I'll see you there. Magnetism definitely is a type of energy, because what happens when you have two magnets really close to each other? They exert a force on each other. One moves the other one, right? So work is being done, so it's definitely a type of energy. There's nuclear energy, and that is the potential energy stored in the nucleus of an atom. You guys, atoms are crazy. They shouldn't work. They shouldn't exist, because you have all these protons next to each other that don't like each other at all, and they're just hanging out there. So there is an insane amount of energy that goes into keeping a nucleus together. And so crazy things happen when we split that atom apart, or when we take two atoms and then smash them together to make an even bigger nucleus. So yeah, that's where we get fission and fusion from. Okay, so fission is these atomic bombs. That's how those work. It's because you split an atom apart, it just gives off an insane amount of energy, because all that energy was stored in keeping it together. And then when you break it apart, it's given off. And then fusion is actually even more energy, and that's what our sun is doing all the time. It's nuclear fusion. It's taking two hydrogen atoms, binding them together to make a helium atom. So that is how fusion works. So that's where sun gets all its energy, and I think we can all agree that sun has a lot of energy. We have mechanical energy, and that's the sum of kinetic and gravitational potential. And I'm not going to go into that because I'm going to do an entire lesson on that. And then we have thermal energy, which is just the form of transfer of heat from a hot object to a cold object. So on a really hot day, the sun has so much energy, and it has to transfer the heat to us. And I know, like, we're really warm, we feel really warm, but compared to the sun, you're still like super duper cold. So it's just going to keep transferring its heat to you. So that's thermal energy. Then we have kinetic energy, and that's the energy of motion. Okay. And then we have gravitational potential energy, and that's just energy due to the fact that something's above the ground, right? So then there's potential for gravity to work on it, and that's the one that we're going to go over way more today. Okay, but just a few notes before we go on to gravitational potential. In any of these transformations, energy can't be created or destroyed. That's impossible. We have a finite amount of energy in the universe, and so all we can do is we can transfer it between objects and transfer the types of energy, right? So for example, look at a really simple circuit with a light bulb. You have chemical energy happening in the battery here, okay? Between different substances that create that chemical energy that makes electrons move. And so then that chemical energy making electrons move makes it electrical energy. And then these electrons are going to be moving along here. And so that's creating new energy, electrical energy. And then it makes it to the light bulb, which then converts that electrical energy into light and heat energy. Okay? So that's a situation where no energy is created or destroyed. It's just being transferred this whole time. Okay? That's a really, really important concept, and one that you'll just keep going over in science because it's just one of the most fundamental things about our universe. All right, so now we're going to move on to potential energy and what that is. So that's just one specific type of energy that I'm going to go over today. So what is potential energy? Let's relate it to the language we normally use. What does it mean if somebody says, oh, you have a lot of potential? Does that mean that you are there? That you have achieved everything? No, it just means that you have the potential or the ability to get there. Okay? And that's such a great way of explaining potential energy as well. It doesn't mean that something actually is moving or is hot or anything like that, but it has the potential to do so. Okay? So it's just energy that's stored in readiness. What the heck does that mean? Well, let's say that I am holding a ball above the ground. Yeah, that's me. So let's actually, make it look like me. First, I gotta have some nice hair, right? Okay, so we'll give me some nice hair. Give me a dress to wear. Woohoo, yeah. Gotta give Miss Waters a nice dress to wear. Okay, there we go. So, obviously, we forgot the red lipstick. We gotta give me some red lipstick. Woohoo. Okay. There we go. Lovely. Okay, so let's say I have a ball here and I'm holding it above the ground. So, of course, here's the ground and here's the ball where I'm holding it. Is there any energy stored in that ball right now? Well, think about this way. By one small change, could it start moving? Could it start doing something? Absolutely. If I let that ball go, guess what? It's going to drop. So there's stored readiness in that ball right now. So it has potential energy. What about if the ball is just sitting on the ground? Doesn't look like it's quite sitting on the ground there, but you get it. Does it have any stored readiness now? It doesn't, because now gravity's already worked on it. It's on the ground. Unless like a big hole opens up in the ground, it's not going anywhere now. Okay, so that's what potential energy is. It's something that has stored readiness to do work. Okay, but really it's only observed once it's formed into some other type of energy, right? We don't know if something has chemical potential energy until a chemical reaction has happened, and then we're like, oh, that had chemical potential beforehand, we just didn't see it. Just like this ball that's just in my hand here, it's not moving, but as soon as you let it go and it starts moving down, you're going, oh, that must have had gravitational potential energy because it started moving when I let it go. Okay? So there's a ton of different other types of potential energy. Another one that you'll go over in physics 20 is spring potential energy. Not that we won't mention it here. We'll still mention it, but we'll go over it in more detail in physics 20. And so basically, what happens if you compress a spring and you just leave it there? Why would that have potential energy? What's going to happen as soon as you let that spring go? It's going to bounce up, right? So you are giving something spring potential energy. This is the same thing that's happening in a bow and arrow, right? You stretch that bow back, and you're giving it that elastic potential energy, or spring potential energy, because of course it's elastic. It wants to spring back to its normal position, and so then it's going to give that bow energy, right, from its spring potential. And then this, of course, is gravitational potential with this big rock up here about to fall down, right? Right here, it might not be moving, but it's kind of teetering on the edge. So one little push and it's going to have kinetic energy. But so right now it has gravitational potential because it has a lot of potential that it could just fall. All right, so we're going to just go over a specific calculation for gravitational potential energy. not all types. Okay, so remember, if we want to calculate this, we can always calculate energy using work, because remember, change in energy is equal to work, okay, which is equal to force times displacement. So if you have the force in a spring and you know how much it displaces something, we can still calculate that spring potential energy, okay? But that's the only way we're going to do it so far. I do just have one other equation to give you for gravitational potential energy though, okay? So the formula for gravitational potential energy is mgh, okay? M is the mass of the object in kilograms. Please do not forget that, okay? It needs to be in kilograms. G, that's just a constant number. That's acceleration due to gravity. This 9.81 here, that's basically if you were to fall, right? If you were to trip and fall, you would accelerate towards the ground at 9.81 meters per second. You're going to do that as long as you're on Earth. That's just how fast your rate of acceleration is towards the Earth, okay? And of course, it's maybe a teensy bit different whether you're at sea level versus up on a mountain, okay? But not enough to really take it into account. So we just use 9.81 all the time. So that's a constant. That's never going to change. G always has to be 9.81, okay? That is on your data sheet, okay? Under constants, you will see it there. And H is the height of the object in meters. Okay, so if something is 2 meters above the ground, then that's H. And then, like all types of energy, gravitational potential is always measured in joules. Okay, from now on, I'm just going to call this EP. Okay, and we're going to leave out the grav because that's just annoying to have to write every single time. But I just want you to keep in mind, remember, there's lots of different types of potential energy. Let's go over a few examples here of how to calculate. So we have an 80 kilogram driver. Now please remember, as soon as you get information, what do I want you to do? I want you to write it down. We were just given mass, right? 80 kilograms. Check your units. Do we want mass in kilograms? Yes, we do. Look at that. He's going to handstand on a 10-meter diving platform. That is high up. Oh my goodness, that makes me nervous. Good for him. So the height is 10 meters. Okay, perfect. Before diving, how much gravitational potential energy does the diver have? Look at that. This one's nice and easy. We have the units and how we want them, kilograms and meters. Okay, how do we calculate gravitational potential energy? Remember, M being mass times G, which is gravitational acceleration, times H. Okay, we have all those, so I have to do nothing but plug in my numbers. So I have 80 kilograms times, remember, G is a constant, always the same as long as you're on Earth. That's 9.81 meters per second squared times my height, 10 meters. Okay, so all you have to do is take 80, multiply it by 9.81, and then multiply that by 10. And if you do that, you get 7,848. What are my units for potential energy or any energy again? That would be joules. Okay, one more thing. So we always need the correct units. What else do we always need? Not direction in this situation because it's a scalar. We need significant digits. Okay, let's take a look. Here we have 80 has 2, 10 has 2. We multiplied, so I just need the smallest number of significant digits, which is 2. So it looks like I'm going to have to change this a little bit. Okay, so I'm going to put the decimal right here. Okay, and I should use the 7 there, and then the 8. And is the 8 going to round up? No, because a 4 is next to it. Okay, so it's just going to be 7.8. But then what do I have to do to the decimal? I have to move it up how many times? 1, 2, 3 times. Okay, so obviously we have to write this in scientific notation. So it's going to be 7.8 times 10 to the 3 because we had to move up the decimal 3 times, and our units are still joules. There we go. Now we are fully complete here. So there's the potential energy. Okay. Let's do another example, but maybe one that's not quite as nice. All right, so we have a 40 kilogram student. Oh, what were we just given? We were given mass. Also in kilograms, yay, that is what we need. Climbs up a ladder to the roof of their house to put up Christmas lights, giving him a gravitational potential energy of 2.00 times 10 to the 3 joules. Interesting. Didn't give us height this time, it gave us potential energy. Okay, and then what are we going to look for? How high is a student above the ground? So we're looking for height. Okay, so what I'm going to have to do is take this equation and rearrange it. So I want you to know how to rearrange this equation for anything. Well, really, it's just M and H that we're going to have to rearrange for. G, we always know G. Okay, G is always going to be 9.81. meters per second squared. Again, as long as we're on Earth. If we're not on Earth, G is not that. But that is another lesson for another day in Physics 20 again. Okay, so what are we going to do? We need to solve for H here. So this one actually isn't as bad as it looks. Okay, what's being done to H? It's being multiplied by M and G. So what do I need to do? I can just divide both sides. I can just divide right here by mg, okay? It's nice and easy. If those are being multiplied, divide that side by mg. Anything you do to one side, you got to do to the other, okay? Those guys cancel out, and you get a nice little equation here. You get that H is equal to potential energy divided by mass times gravitational acceleration, okay? So let's calculate this. So we have my potential energy, 2.00 times 10 to the 3 joules, divided by m times g. So mass is 40 kilograms times 9.81 meters per second squared. And all I'd say about this is careful how you put this into your calculator, okay? Make sure that you put the denominator in brackets, okay? So I would do 2.00 times 10 to the 3 joules, or well, yeah, 2 times 10 to the 3. And then divided by, and then put open bracket, and then 40 times 9.81, and then close the bracket, and then press enter, okay? If you just put it left to right, it's gonna do the division before the multiplication, which is gonna be a problem. Okay, so if we do that, we get 5 well, I get 0.96, so I want to just stop here and make sure I know where to round. Okay, I have 2 significant digits in the 40 and 3 in the 2.00, because remember we do not look at the times 10 to the 3 for significant digits. So, and I'm doing multiplying and dividing, so therefore I just need the amount of significant digits. Looks like 2 is the smaller amount, so my answer also needs to have 2. So here, 5.09 will round up to 5.1. Height, well, what units do I need for that? I need meters. And there we go, we are done. See, it's not so bad, was it? Okay, good, because we're gonna do another one, but now where we have to solve for mass. Again, pause this right here. Type that into your calculator, make sure you get the same thing as me, just so you know how to type it into your calculator, okay? So, Canadian Grey Jay has 47 joules of potential energy. Okay, so again, I'm going to write that down. That just gave me the potential energy, 47.0 joules. Let's just take note that that's 3 significant digits right now. All right, and that's when it's perched up at a tree at a height of 5.99 meters. Fun. Okay, so my height is 5.99 meters. Also 3 significant digits. So I'm guessing our answer is going to have to also be 3 significant digits. So we are looking for the mass of the Grey Jay. Don't forget, we always also have gravitational acceleration, which is 9.81 meters per second squared. Okay, so again, we have this EP equals mgh. So just like when we were trying to solve for h, now we're trying to solve for m, but basically the same thing's being done. M is being multiplied by g and h, so it needs to be divided by g and h to be able to solve for it. And that does cancel those guys out. Anything you do to one side, though, you have to do to the other. So what we get for mass is EP divided by GH. Okay? So these ones are actually really, really nice to rearrange. Basically, if you have to solve for M or H, just divide by the other two. Okay? And that's all it's ever going to be. So it's actually a pretty easy one to rearrange. Okay, so my potential energy was 47.0 joules. I'm dividing by G times H, so that's 9.81 meters per second, times the height, which is 5.99 meters. Again, when you're typing it into your calculator, make sure you put the denominator, the 9.81 times 5.99, in its own brackets. Okay, and what do I get? Well, I'm going to write this out first, actually. I'm not going to round it right away because this is one that a lot of people have a hard time with. So this is what I actually get, but I wrote down 4 significant digits. I don't know if you guys noticed it. There's 7998. Okay, so how the heck do we write this to only 3 significant digits? So this is such a tricky one because rounding is not going to be fun. So of course there's an 8, so we have to round the 9 up. How do you round the 9 up? Well, you got to go to the next one and make that the next whole thing. But then that's a 9. So then we have to round the next thing up. So that's going to be rounded up to an 800. So what I would do is think of if you had 799 and you had to round that up. What would you round that up to? 800, right? If you had to round it up to the nearest 100. Well, it would be 800, obviously. So that's something you can do to know how to round this, because we need to round it up to the nearest 100th, because we're looking for 3 significant digits, and the first digit is a 0. So this 0 is not significant. So therefore, what does this look like? Well, there's an 8 there, and to make sure that I have 3 significant digits, I need to put 2 zeros behind it. Now I have 3 significant digits, and that's kilograms. Okay? So just be really careful about that rounding. I think a lot of you guys are actually doing quite well with the calculation part of it, which is so awesome. I'm really excited about that the calculations aren't tripping you up too much. It's so many little things like that. It's rounding, it's forgetting units, it's, having trouble with the significant digits. So honestly, I know it's frustrating, but just keep at it and you'll get so much better. The fact that you can do the calculations is the biggest hurdle right now. And I'm really excited that you guys are actually doing quite well with that. If you want to do a little bit more practice, okay, you do have the pages in the workbook that we're going to give you, but here's a few more practice problems in your textbook as well, just if you do want to practice a little bit more. It is very good to just practice, okay? All right, before I end, I just want to talk a little bit about the difference between mass and weight, because so many people use them interchangeably and they shouldn't, okay? Mass is how much matter is in you. Weight is how much gravity is pushing down on you. And we often use weight to mean mass, okay? When people are like, oh yeah, what's your weight? And you say however many pounds. I'm not saying how many pounds I am, thank you very much, or kilograms. And that's what you say, but no, that's mass. Mass is measured in kilograms. Mass is measured in pounds. Weight is actually measured in newtons, because again, it's how much gravity is pushing you down. So weight is actually the force of gravity on you or on whatever object that has mass. Okay? So the mass of an object just refers to the amount of matter it has, okay? And that's it. It's measured in kilograms. You can measure it in pounds or grams or whatever, but we like to measure it in kilograms in physics. And of course, the weight is really just the force that the Earth is applying to that object. So therefore, your weight on the moon will be a lot less than your weight on Earth because there's not as much gravity on the moon. Okay? So we actually have an equation here that we can create because we know that force is equal to mass times acceleration. Okay? But what's the acceleration due to gravity on Earth? We know, we just learned that. It's 9.81. So if I replace acceleration with gravitational acceleration, I put g there. So F is equal to mg instead of ma. But this, of course, is only the force due to gravity. So we have to put this little g down here. It's called a subscript, okay? A lot of people want to write it like this, saying Fg. No, the F is a little subscript, so you got to write it tiny like that, okay? Just saying, and that's all we use that for, is just to say, oh, this is the type of force I'm talking about, okay? So Fg is the force of gravity, and that's measured in newtons. M is the mass of the object. G is the acceleration, okay? So just so you know, that's what weight is. So as I mentioned, there are tons of different types of potential energy, not just gravitational, okay? But unlike gravitational, they don't necessarily have a special formula. Just gravitational potential energy does, at least for science 10, okay? But really, we know whenever work is done, well, that gives it potential energy, okay? Work is done, it gains potential energy. And that can just be used using the formula we've seen, that work is equal to force times displacement, because again, we know work is equal to the change in energy. So we can always also calculate energy just by using the work formula. Okay, so work done on an object means it's giving it potential energy. So for example, say I want to actually calculate elastic potential energy. You're like, Miss Waters, we're not doing that. You said that we don't have to do that till physics 20. We don't have to do that with a special formula until physics 20, but we can still do that here in certain situations. So we have an athlete stretching a resistance band 0.20 meters. So that means it's done work. The athlete has done work, and so it's given this air resistance, or this resistance band, potential energy. Okay? And he uses a force, or she uses a force of 50 newtons. So I want to know how much elastic potential energy does the tubing have? Well, here I can't use the elastic potential energy formula, but what I can is say, oh, well, I know change in energy. Here there is a change in energy, right? It's giving it potential energy is equal to work, which is equal to force times displacement. I have force and I have displacement. I can absolutely calculate the potential energy here. Okay, so this potential energy can just be force times displacement, which is just 50 newtons times 0.20 meters. If we calculate that, we get 10, do you guys remember? Joules is the units for energy for work. Okay, so don't let that trick you. When I say calculate potential energy, it's not always going to be MGH, okay? That's only for gravitational potential energy. So here it says elastic potential. Well, in that case, just remember, oh, right, there's another way to calculate energy, and that is using work. Okay? So please, please, please don't forget that. But again, practice makes perfect. Just go practice. Always write down what you have. That's something I didn't do in this example. Bad, Miss Waters, bad, right? Because you need to say, oh, well, it was moved to distance of 0.20 meters. It was given a force of 50 newtons. And then when you do that, you look at what you have and you say, oh, I think I know what formula to use. Okay? So it's always looking at what you have, look at your formulas, say, which one can I even use in this situation? Oh, work equals force times distance. Looks like a good one. Oh, work is equal to change in energy, and I have to calculate how much energy was given. So perfect. Okay? Well, that's it. You guys, good luck with gravitational potential energy. Okay? And if you have any questions, please comment below, email, anything you need to clear anything up, please just ask. Okay?